Hi, in this section we are going to be talking about how do we compare the results of our supervised learning exercises and what kind of errors are possible during this exercise. So when you want to compare the results of a training exercise and testing exercise, what you build is what is called a confusion matrix. I don't know why they called it a confusion matrix, but that is what you build. How is a confusion matrix built is that it plots the predictions against the actuals for the test data. So you basically build a model with the training data set, then use that against the test data to actually test the model. Then you plot this confusion matrix in which the actual values of the outcomes or the target variables are plotted here as columns. The values in this particular case, it is a Boolean outcome. It is a true or false outcome. Maybe we are trying to predict patients who have a specific disease. So the actuals are plotted as columns here, true or false, and what you predicted is plotted as rows here, true or false. So here trying to compare the actuals to the predictions, and then you fill out this particular table as to how many actuals you predicted correctly, how many actuals you predicted incorrectly. So this is what you call as the confusion matrix. The confusion matrix tells you the correct predictions and the incorrect predictions. What you see in this diagonal here is the right predictions, where you predicted true as true and false as false. The ones you see here, 6 and 9, are incorrect predictions. So when you do a testing exercise, you take your model and apply it on the test data. Then you build this confusion matrix to understand how accurate your algorithm is, and this one clearly tells you where your algorithm is going wrong. In this case, it's only true or false, but sometimes this might even be categorical data like excellent, good, very good, etc., things like that. So you will look at where exactly it is going wrong. Like it might be going wrong, whether in terms of, sometimes what happens is it may be predicting false, all the false as false, but sometimes it may be predicting trues as also false. Like this might be high, this might be low. So those kind of differences will happen, and you have to take a deeper look at this confusion matrix to understand how your predictions are working. So these predictions, of course, can be Boolean or classes, and we would see both kind of confusion matrix as a part of our case studies. So what are the various prediction types? So when it comes to the confusion matrix, there are certain terms that are being used in the real field, and you would have heard about this a lot, about false positives and true positives. Especially in the medical field, these terms are highly used. So let us try to go and understand what these are. So if you look at the table on the right side, you see what is a true positive. A true positive is a right positive. That is what is called a true positive. You are correctly, true here stands for the accuracy, and positive is basically the outcome. So you say here a true positive is you correctly predicted the true here. A false negative is something that is a true you predicted as false. So this is what is called a false negative. Then you have a false positive, where something is a false and you incorrectly predicted as true. And then true negative is a correct prediction of negative. When you say true in the front, it means that it is correct prediction. When you say false in the front, it is incorrect prediction. So these are the terms that are used to define each of these boxes, and these boxes actually play a very important role when you are discussing prediction outcomes. True positive and true negative, of course, is those are the ones expected, but you have to focus on false positives and false negatives more to understand the accuracy of your predictions. So false positive, why these false positive and false negative are important is that sometimes it is about what is acceptable and what is not acceptable. Sometimes, depending on your use case, false positives are okay, but false negatives are not okay. In some other field, false negatives are okay, but false positives are not okay. For example, in the medical field, you're trying to do some tests, and then you're trying to predict whether a patient has a disease or not. A false negative in a medical field is critical, which means somebody has a disease, the actual is true, but the actual is true here, but you're trying to predict as false. So somebody really has a disease and your prediction algorithm predicts as false. Now that is unacceptable. You do not want false negatives. That means you are not going to be treating someone who has a disease, and that can be really fatal. So false negatives are not acceptable in a medical field. False positives are acceptable. Okay, somebody doesn't have a disease. It predicts that the person does have a disease. Okay, you take that person as a patient. Usually you will do more tests and figure out, okay, this guy doesn't have a disease. That's okay. But false negatives are not acceptable. False positive are not acceptable, in the judicial field. What that means is somebody has not done a crime, and you are predicting that somebody has done a crime. And that is again serious. You are predicting an innocent person as a criminal. That kind of prediction, again, not acceptable. So it depends on the use case as to which one is acceptable and which one is not acceptable. Some formulas or some confusion metrics that you keep hearing and which you would be using a lot in the data science parlance are these. So first thing is accuracy. How do I measure accuracy of a prediction? Is basically taking true positive and true negative, that is my correct predictions, divided by the total number of samples. So you have all of them are samples, the count of the number of samples, right? So you say true positive plus true negative divided by everything else. True positive plus true negative by divided all of them. Please commit all these formulas to memory, because if you are going to interviews, these are the questions that they may typically ask you. Sensitivity is how good are you in predicting the true positives. So if you say sensitivity equal to true positive divided by true positive by false negative. So sensitivity is about this column. Then comes specificity. Specificity is about the false column. So you are taking true negative here and dividing by true negative plus false positive. So specificity is about this false column. Then comes precision. Precision is about this column on the this row, the true row. So it is true positive divided by true positive plus false positive. So these are the various formula that is used to define the accuracy of your predictions. Typically, as I said, these are some things typically you will find in interviews. You get asked these kind of questions. Prediction errors. So what kind of errors do you get in predictions? There are two types of errors you want to worry about. One of them is called bias and the other is called variance. So what is bias? Bias happens when the model skews itself to certain aspects of the predictions while ignoring others. What do you make it skewed? And when this is a little complex explanation, so let me give you a nice example. Suppose you have you are trying to predict the age of a person, okay? And when you try to actually do a test and trying to predict an age of the person and trying to find the difference between the prediction and the actual, you will see that the difference is always somewhere around -5. The difference is always like -5, -3, -4. It is actually skewed towards that -5 range. So everything it is trying to predict is around that -5. The difference is always around -5. That is what is called bias. So you see here this is an example of high bias, and in that high bias you see that instead of hitting the target in the middle, it is always skewed towards one end. So it is always around this -5, -6, -4 kind of thing. Variance, on the other hand, refers to the stability of a model, or how accurate or close it is trying to always predict. What I mean again by variance is, let us say the same example of age. When you are trying to predict the age, what is the error? Now the error might here be all over the place. For one it is -5, the next person it is +5, then there is a 3, then there is a -6. The error is all over the place. So that is called variance. And in the chart on the right side, you see a comparison of what is high bias and low bias and what is high variance and low variance. Ideally, you want to be in the bottom left corner where there is low bias and low variance. So high bias, you see the whole thing is like skewed towards one end. Variance, on the other hand, you see a high spread. There is a spread of the prediction that is happening. Whereas in the case of low bias and high variance, again, there is spread happening, but the spread is around the center. But you have high bias and high variance, the spread is again skewed. There is high spread and high skewing that is happening. So bias and variance are two important aspects that are discussed when you are trying to discuss various machine learning algorithms and how good these machine learning algorithms are. There are certain machine learning algorithms that tend to have high bias, that tend to have high variance. So these are the things you want to be watching out for. Types of errors that are faced during a prediction algorithm. The first thing is in-sample error. In-sample error happens. What is in-sample error is, you go build a model in supervised learning. Then you use the model on the training data set itself. So you build the model on the same data you built the model off. So you apply the model on the same data set you built the model off. So you apply the model onto the training data set and see how much this model can predict the data from which it is built off. Ideally, given that the model is built off the training data set, it should be very accurate on the training data set itself. And that error is measured as in-sample error. So if the model has high in-sample error, that is something really bad that is going on. Either there is not enough signals in the data or something like that, because at least at the minimum, the model should predict the training data set accurately. Out of sample error is basically everything else. So when your model is used to predict on a new data set, like a test data set or a real life data set, what is the error that you get in terms of predicting the actuals? That is called out of sample error. Overfitting is a concept that refers to a situation where there is very low in sample error but very high out of sample error. What that means is the model, when you try to use the model to predict the training data set itself, it has very low error. But when you try to predict a new data set, it has very high error. What that means is the model has overfitted itself into the training data set. If you look at a data set, the data set has signals, good signals, and the data set has noise. It also has a lot of noise in terms of it shows some false patterns, false trends too. And then the model tries to adapt too much itself into the training data set. It models both the signals and the noise. But what happens when you go into a new data set? The new data set is going to only retain the same signal characteristics, but it may not retain the noise characteristics. So when it tries to predict on the new data, the error that you're going to be getting is pretty high. So that is what is called overfitting. It has very low in sample error and very high out of sample error. And this is something that happens when the data set you use is very small. One, you might be not having enough amount of data to characterize everything that is happening in the real world. Second is the training data set is not a reflection of the situation that you are trying to predict. For example, you take data about your phone customers and then you try to predict how your web sales will be. So if the patterns of phone sales and web sales are different, obviously the model that is built on your phone data set is not going to predict your web data set very accurately. So those are the reasons. Those are some of the reasons why you might have overfitting happening when you are trying to do a machine learning predictions.